Okay, so in the last section we derived the equation of motion for a charged point particle by varying an action. Now today we want to verify that this equation reduces to what we expect from a non-relativistic mechanics and Maxwell theory. So the equation that we obtained in the last section was m times dx mu d2x mu d tau squared is equal to q times f mu nu dx nu d tau.
Absolutely.
We want to take the non-relativistic limit of this equation. So what is the expression for dx mu d tau? This is the forward velocity, which is gamma and gamma v. In the non-relativistic limit, this goes to 1 and v. So we would like to look at the spatial component of this equation to get the acceleration. So if we look at the spatial component of the left side, we get the usual acceleration. Moreover, this one means that the proper time and the usual coordinate time are the same, because this component is just dt by d tau, dx0 by d tau, which becomes 1 in this limit. So my clock is measuring which is measuring the proper time, it is also measuring the absolute time, or the coordinate time. So for the ith component, we just get the second derivative of the position, which is the acceleration. And then on the left hand side, we will have fi q times fi nu dx mu d tau, which again we are going to substitute. We also use the fact that in our signatures, in this, the special indices of up and down are the same, because we are using mostly plus signature for the metric. So this is just q fi nu. Now let's expand in the components. So for nu equal to 0, we just have 1. So fi 0 times 1. And then when nu is running over special indices, we will have Vj.
And an effective scheme if you're going to non-relativistic case can be that just neglect the second powers of the velocity. Because if we compute the dot product of four velocity here, we will get 1 minus v square, and if we neglect v square, so we will get again one minus 1 plus v square. So we will get minus 1 again, which should be minus 1, because we know that the dot product of four velocity itself is always minus 1. So can we say that just neglect the second powers of v if we want to go to non-relativistic cases?
Yeah, so here v is the small parameter in the non-relativistic limit. So yeah, I guess here it would be the right prescription. If you were to calculate the kinetic energy, you wouldn't want to neglect the second power of v. So you want to keep the leading expression in expansion in terms of velocity.
For example,
and that leading.
For example, I can ask that in the time component of four velocity, if you expand gamma in terms of in the powers of v square, and v square is the leading power, then why are you neglecting that?
In the four velocity, you say?
In the four velocity, the time component, gamma is 1 over v.
Well, no, the leading term is 1. Then v squared will be the subleading.
So, actually I was asking that question because you wrote just one in the time component.
Uh-huh.
So you didn't neglect
No, I just kept the leading term in the expansion in terms of velocity.
By leading term you mean any, I thought the leading term in V. The
Well,
leading term in V would be V square.
No, the leading, okay, so this is a matter of terminology, I guess. But I think the standard terminology is that if I have a small parameter and I expand in that a small parameter, the leading term is the first term in the expansion. That can be 0th power, can be -1 power, can be second power. The first term in the expansion is the leading term in the expansion. Yeah.
Because some people don't count 0th power as the leading.
No, leading is always the leading, the first term in the expansion.
If you take the second order term, you are already wrong because that's much smaller than the other component. So leading order is pretty much no. There is no order 1 term for the first component. You only keep the 1. That's there is no order 1 in B for the first component.
Right, there is no order 1.
So at order B, the only term that survives is 1. Same. There shouldn't
Yeah,
be
if
any
you want,
reason
if you
take
decide
it
to
this way.
keep up to order V, again the answer here would be
It's the
to
same.
keep 1. But here what I'm doing is that I'm just keeping the leading term in this expansion in respect to velocity. So in a sense, the magnetic force here is subleading because it's compared to the electric term this is suppressed by 1 factor of V. But here I'm doing, this expansion is a consistent expansion. So I'm keeping, here this will be the leading term which is proportional to the magnetic field. So if I had another term including the magnetic field, I wouldn't keep that, but this is the first term that includes magnetic field and then that comes with the velocity. Okay, so in fact, now we want to express these objects in terms of the electric and magnetic field. So how do we do that? We know that F mu nu is equal to d mu a nu minus d nu a mu. Fi0 is equal to di a0 minus d0 ai. We know that A0 is minus the electrostatic potential. So we get this expression for Fi0, and this is nothing but the electric field. This is ER. And if I look at Fij, which is di aj minus dj ai, this is epsilon ijk times bk. You can verify it by looking at the xy component of this object and see that that gives you the correct expression for the magnetic field in z direction. And now if I plug these two expressions in here, I will get q times ei plus v cross p r, which is the Lorentz. Questions? Okay, so now we want to move to the next topic, which is the Northern Theorem. So we talked about variation principle and how to derive equations of motion from action. So we said that in order to describe the physics, we identified the relevant degrees of freedom, and we write the most general action which is compatible with the symmetries for those degrees of freedom. And if we do variation of that action with respect to those degrees of freedom, we get the equations of motion and dynamics, which govern the dynamics of the system. Now there is a very important theorem called the Northern Theorem that allows us to connect symmetries of the action to conserved quantities and conservation laws. Like for instance, energy momentum conservation is related to the symmetries of the action with respect to the space-time translations. So for instance, we want to discover that connection and derive the associated conserved quantity. And that's the content of the Northern Theorem. Maybe I erase.
There's one question that I had in mind since the day when I came up with this, came across this equation. What about the zeroth component of this equation? Because it tells you something that the dot product of electrical field with the current vector is zero. What is the meaning of that?
The zeroth component of this equation. So you want to say mu equal to 0, right? Okay, we can try to see what we get. So now we want to take the non-relativistic limit. Okay, so in the non-relativistic limit, the zeroth component becomes the derivative d by dt of gamma, which is, in fact, this was plus 1. 1 plus 1/2 v squared. And then on the right hand side, I have q. Let's bring down this index. So f0. And since f mu nu is anti-symmetric and I have 1 0 index, the other one should be a spatial index. So I get f0i times dxi d which is the velocity, vi. And now f0 minus f0i is just the electric field. So here I get q times v dot the electric field. And what else can I do? What I can do is to, well, this one is irrelevant. But the left-hand side of this equation is just giving you d by dt of the kinetic energy of the particle. Right. And then, yeah, so it just tells you that the change in the kinetic energy is equal to the work done by the electromagnetic field.
And because magnetic field doesn't do work, that's why it doesn't appear.
Right. So this, in general here you would write V times the force. So this force is Q times E plus V cross P. But V dot V cross P is 0, so you just get Q times V dot E. This is just a conservation of energy. which is the first integral of your special equation. So if I take the equation of motion, find the first integral of that, I will get the conservation of energy.
Actually, I was confused because on the left-hand side, I was just taking the leading term 1. That's why I was getting 0 here. That's why I was confused. That what is the meaning of this equation? So, but I have to take v square as well. Okay.
Okay. Other questions?
Why didn't you discuss it before?
Sorry, say it again.
Why didn't you discuss this part?
I don't know. I never thought about it. Maybe next year I discuss. Okay, Northern Theorem. Okay, so we want to start from some theory which has a variational description. So we have an action for some degrees of freedom that I call them phi, but it doesn't have to be just a scalar field. This is just the general notation that so what I'm going to say about the Northern Theorem is very general. It's not limited to 4 dimensions and it's not limited to a scalar field. But just for notational simplicity, I use a field phi in 4 dimensions. So what is the statement? We want to first define what do we mean by a theory that has a symmetry. What do we mean by symmetry of this theory? What we mean by symmetry of this theory, and I'm going to talk about continuous symmetry, so symmetries that can be performed infinitesimally. They have some small parameters. I'm not talking about discrete symmetries, but continuous. So I want to send phi to phi plus some delta S phi. So some infinitesimal change in phi, which is prescribed. And the symmetry of the action would be if I do this substitution in here and linearize in delta S phi, then the change in the action is a total derivative. So it's d mu of some lambda mu. Now this lambda mu can be 0, but it doesn't have to be 0. So when this happens, we say that this is a symmetry transformation. So let us see some examples, because this looks a bit...
Are you talking about the classical level?
Say it again?
Are you talking about the meaning of having a symmetry at the classical level?
Having a symmetry at the classical level. Yes, if you are worried about anomalies, don't worry about them. Yeah, this is classical. Otherwise, you would ask about you would ask the path integral to be invariant under the transformation. So yes, so let's consider some examples. For instance, we can have the scalar field, if a massless scale, free massless scalar field. So imagine the action is given by d4x d phi square minus 1/2 d4x d phi square, and the symmetry of this action is phi going to phi plus a constant. This is obviously a symmetry because every phi in here is acted on by a derivative. So therefore the change of the action under this transformation will be just 0, which is a particular case of being a total derivative. So this is kind of a trivial case. A little bit less trivial is in the same theory I have another symmetry, which is if I send phi to phi plus some constant for vector times x mu. This is called, sometimes it's called Galilean symmetry. Now let's work out what happens if I make this transformation. So now delta b of s is equal to minus integral d for x d mu of phi d mu of d mu x mu, which is equal to minus integral d for x d mu times d mu phi, right? Which is a total derivative because I could just write it as d mu of d mu phi. Remember, b is a constant. Is a constant for vector. So now the change of the action under this transformation is not 0, but it's a total derivative. So this is called a symmetry of the action. Another example is a space-time translation. So now I take phi to go to phi plus some constant for vector times d mu of phi. Now we can this is a symmetry even if we have a massive field. So let's take a massive theory, d for x d phi squared plus m squared phi squared. This is the action now. And the change in the action is minus integral d for x d mu phi d mu phi plus square phi d mu phi. So I just plug that and I linearize in this parameter A. That's how this factor 1 went away. And then we do a little bit of manipulation. So again, remember that this A is just a constant for vector. So what we get is minus integral d for x. I factor out a mu. So here I have d mu phi, d mu phi, and here I have m squared phi d mu phi. This delta A of S is equal to, okay, so now this object I can write it as 1/2 d nu of d phi squared And this I can write it as 1/2 d mu of phi squared. So I will get the following. I will get d4x a nu d nu of minus 1/2 d phi squared minus 1/2 m squared phi squared. And again, since a is a constant, I can put it inside. And as you see, this is a total derivative. So again, it satisfies our definition of a symmetry transformation. Therefore, this is a symmetry of the action. In fact, any action that we write for any kind of field that doesn't explicitly depend on the space-time coordinates, it will be invariant on the space-time translation. So this was one example. Okay, so this, so we define what we mean by having a symmetry of the action. Now, when we have a symmetry of the action, then it has the Northern Theorem tells us that it leads to a conservation law, and we want to derive that conserved quantity. So there is a following prescription to derive that conserved quantity. How do we derive it? Let me just write this here. So here we found the nu of a nu times basically the Lagrange. So we want to derive the Northern current. Here we just talked about what we mean by symmetry. So imagine now we have identified the symmetry of the action. Then we do the following trick. So suppose we take phi to phi plus some epsilon of x times delta s of phi. Of course, everything here is a function of x. I'm writing epsilon of x here just to emphasize that it is a function of x. But also delta s of phi is a function of x. And phi is a function, it's a field, so it lives in space. So I multiply my symmetry transformations by some space-time varying object, varying function, epsilon. This has the following property. I want this epsilon to be localized, so that when x goes to infinity, epsilon is equal to 0. So epsilon is some arbitrary localized function. And we want to plug this in the action. So let's ask what happens if I plug this in the action, in that same general action that had the symmetry. Now, we want to plug this expression in. And what we find is that there's going to be two terms in here. One of them is similar to what we had before. So I get the mu of epsilon times lambda mu, because I modified my transformation by epsilon, I'm linearizing it. So we get a boundary term, or a total derivative term. But this total derivative term is now irrelevant, because epsilon is vanishing at infinity. So if I this total derivative term reduces to a boundary term, but at the boundary epsilon is equal to 0. So this is irrelevant. But there will be another term, because now I have changed the transformation. It's not the usual, the original symmetry transformation. This extra term will be, it has to be proportional to the derivative of epsilon. And then the proportionality constant, or proportionality function, I will call it J mu. Why should it be proportional to d mu of epsilon? Because if epsilon was a constant, I would go back to the original case. So I would need to get just the total derivative, just by the fact that this original transformation was a symmetry. But this has to be the structure of the change in the action if I perform the following transformation. The total derivative term plus a term that has the derivative of epsilon. But we said that the total derivative term is irrelevant because of the fact that epsilon vanishes at the boundary. So we only have this term. Now can we say something about J mu? And the answer is yes. J mu has to be conserved because has to be conserved on shell when the equations of motion are satisfied. Because this transformation is for arbitrary epsilon is a particular variation of the action, right? And we know that the action is stationary on the arbitrary variations when the equations of motion are satisfied. So when the equations of motion are satisfied, the variation of action has to be 0, which means that, so again I can do an integration by parts here. This time I dropped. There is d mu j mu plus again a total derivative term that I can drop because epsilon vanishes at infinity. So I end up with this, and we know that when the equation of motions are satisfied, requires on shell, then delta S has to be 0, which means that d mu j mu on shell has to be 0. So this J mu is called the Northern current, and the fact that d mu of J mu has to be 0 when the equations of motions are satisfied is called the Northern Theorem. Let us consider this example. So the simplest one is here. Suppose now I do this transformation, shift of phi, but now I want to promote this shift of phi to be multiplied by some epsilon of x, promote it to be a local function. Now I could I could write it as phi going to phi plus epsilon of x times c, but this is a bit redundant. I just write it phi going to phi plus c of x. So I just promote the parameter of transformation to be a function, a localized function. So now let us see what happens if we vary the action, do this variation of the action. We get d mu of phi, and now we have d mu of, so this is the change, here we have c. Before this c was a constant and this derivative was 0, but now it's not a constant anymore, so we get d mu of c. So now you see that we actually end up with this situation. the variation of the action is now contains a term which is proportional to d mu of our parameter or transformation parameter is C of x. And what is multiplying it is another current, now with lower index. And the statement, the claim is that d mu of j mu is 0 when the equations of motions are satisfied, which is indeed the case because d mu of j mu is nothing but box phi, which is 0 when the equations of motion are satisfied. In fact, it is the equation of motion for phi. Okay, I don't do the second example, I just do the third one. Second one is left as an exercise. And let's see if I can do it. Alright, so now again we want to do this transformation, except that we want to multiply by an arbitrary function here. Again, instead of multiplying this by an epsilon, I just promote this a mu to be a function of x as opposed to a constant. So I keep track of derivatives of a mu. And we go through the same exercise. In fact, part of it is already correct because here I didn't, at this point I haven't assumed that a mu is a constant. So we have that we have phi going to phi plus a mu of x times d mu phi, and we ask what is the change of the action, and we get minus d4x, and we have d mu phi, and I'm going to just expand this derivative. So here there will be two terms. There will be d mu a mu times d mu phi, because now the derivative can act on a mu, and then the other term would be a mu d mu phi. This is what we had before. And then there will be the part from the mass term, which is m squared a mu m squared phi a mu d mu phi. So now this term is already the derivative of our transformation parameter, so it's of this form. So I keep it. And this other ones we can manipulate a little bit. So there is d mu a mu times d mu phi d mu phi. This part remains there. The other piece is a mu. So this is what we had before. So the other piece is 1/2 a nu d nu of d phi squared plus m squared phi squared. Now, again, I can freely do partial integration because now A is a space-time variable and it vanishes at the boundary. So this is equal to minus integral d4x times d mu n nu in fact, let me write it like this. D mu n nu, then I have d mu phi, and then here I'm going to do a partial integration. I get the minus sign. And then there will be a Kronecker delta because it's d mu of a nu. While here I have d mu and nu, so there is a Kronecker delta, and then the rest is d phi squared plus m squared phi squared. And then there are some boundary terms that I said they vanish because A is going to vanish. Now this is again of the same form as this equation, except that now our transformation itself had a label, had a space-time label mu. So we really have 4 symmetries here, not only one. These are translations along every space-time dimension. So here we are going to discover not only one conserved current, but 4 conserved currents, which are labeled by this index mu. And there they are. These are called, they are collected together into this tensor, which is called the energy momentum or stress energy tensor, given by d mu phi minus 1/2 eta mu nu times d phi squared plus m squared phi squared. This has to be constant.
Delta instead of
Delta.
Sorry, delta. Yes, so this is called the energy momentum tensor, which is conserved when the equations of motions are satisfied. This we can easily verify that the mu of t mu nu is proportional to the equation of motion for phi. And therefore it is 0 when the equations of motions are satisfied. Okay, maybe you can try to do an exercise. Is there 2 there? Who doesn't have?